A first-of-its-kind signal has been detected in the human brain. Scientists have recently identified a unique form of cell messaging occurring in the human brain that's not been seen before. Excitingly, the discovery hints that our brains might be even more powerful units of computation than we realized. Back in 2020, researchers from institutes in Germany and Greece reported a mechanism in the brain's outer cortical cells that produces a novel graded signal all on its own, one that could provide individual neurons with another way to carry out their logical functions. By measuring the electrical activity in sections of tissue removed during surgery on epileptic patients and analyzing their structure using fluorescent microscopy, the neurologist found individual cells in the cortex used to not just the usual sodium ions to fire, but calcium ions as well. This combination of positively charged ions kicks off waves of voltage that had never been seen before, referred to as calcium-mediated dendritic action potentials, or DCAPs for short. Brains, especially those of the human variety, are often compared to computers. The analogy has its limits, but on some levels, they perform tasks in similar ways. Both use the power of an electrical voltage to carry out various operations. In computers, it's the form of a rather simple flow of electrons through intersections called transistors. In neurons, the signal is in the form of a wave of opening and closing channels that exchange charged particles such as sodium, chloride, and potassium. This pulse of flowing ions is called the action potential, and instead of transistors, neurons manage these messages chemically at the end of branches called dendrites. The dendrites are central to the understanding of the brain because they are at the core of what determines the computational power of single neurons. Humboldt University neuroscientist Matthew Larkham told Walter Beckwith at the American Association for the Advancement of Sciences in January 2020, dendrites are the traffic lights of our neuron system. If an action potential is significant enough, it can be passed on to other nerves, which can block or pass on the message. This is the logical underpinning of our brain, ripples of voltage that can be communicated collectively in two forms. Either an and message, if X and Y are triggered, the message is passed on, or an or message, if X or Y is triggered, the message is passed on. Arguably, however, nowhere is this more complex than in the dense, wrinkled outer section of the human central nervous system, the cerebral cortex. The deeper second and third layers are especially thick, packed with branches that carry out higher order functions we associate with sensation, thought, and motor control. It was tissues from these layers that the researchers took a close look at, hooking up the cells to a device called a somatodendritic path clamp to send active potentials up and down each neuron, recording their signals. There was a eureka moment when we saw the dendritic action potentials for the first time, said Larkham. To ensure any discoveries were not unique to people with epilepsy, they double-checked the results in a handful of samples taken from brain tumors. While the team had carried out similar experiments on rats, the kinds of signals they observed buzzing through the human cells were very different. More importantly, when they dosed the cells with a sodium channel blocker called tetrodotoxin, they still found a signal. Only by blocking calcium did they fall quiet. Finding an action potential mediated by calcium is interesting enough, but modeling the way this sensitive new kind of signal worked in the cortex revealed a surprise. In addition to the logical and or type functions, these individual neurons could act as exclusive and XOR intersections, which only permit a signal when another signal is graded in a particular fashion. Traditionally, the XOR operation has been thought to require a network solution, the researchers wrote. More work still needs to be done to see how D-caps are behaving across entire neurons and in a living system, not to mention whether it's a human thing or if similar mechanisms have evolved elsewhere in the animal kingdom. Technology is also looking at our own nervous system for inspiration on how to develop better hardware, knowing our own individual cells have a few more tricks up their sleeves could lead to new ways to network transistors. Exactly how this new logic tool squeezed into a single nerve cell translates into higher functions is a question for further researchers to answer. The research was published in Science magazine, originally in an article from January 2020, and this is on Science Alert by Mike McRae. Please leave your comments. Thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.